Okay, we have Sam up there graphing these by hand. I want you to do both of them. Well, actually, just do the top one. Okay, so Sam seems to think that this is how you graph it by hand. Why is it, Sam, that you are over there at comes down at hits the graph over there on the right side? 1, 2, 3, 4, 5 about. Okay, why did you draw an exponential line? Is x squared? Yeah, that's quadratic. Okay. What about the left side of that graph? If that's okay, go back and do it with quadratic. Yeah, because I think you did get you got exponential mixed up with quadratic. That's quadratic. What do you want, or do you want another volunteer? Okay, I'm gonna have. Yeah, no, just erase that one. You're gonna do the top one. Hey, you guys, please listen, so you can learn from this. Sam would have had it right if it was exponential. He was thinking exponential. That would have been actually correct. How many of you guys made a table of values? Okay, Julie did. Okay, what do you guys think? What do you guys think about that? Okay, Brain he thinks it's supposed to touch at 0. What do you guys think?
I agree.
Okay. I think Braden might be right. That's a pretty good graph. Julie made a table of values. It's just that she's missing the point where it comes down all the way and touches the x-axis. So that's pretty good. Okay. I'm going to talk about this one for a second. Some of you, sounds like you have it, but let me show you guys maybe even an easier way to do this. A table of values is going to be used a lot for a quadratic equation. But if I was graphing a quadratic equation where it was x squared minus 5, we all know that a quadratic equations look like this. You're going to have 0, 0, 1, 1, 2, 1, 2, 3, 4, because you're squaring it each time, right? 3, 9. And then you got the ones going in the negative direction. -1, 1, -2, 4, -3, 9. And you have those points, and your graph comes down like this. That's what you would have if you graphed just x squared. Y equals x squared, right? But then, if we use some transformations to get that, we can then move that graph down where? Where would we move it? If we added the x squared minus 5, y equals x squared minus 5, where would that take the graph to? Huh? No, just the x squared minus 5, not the absolute value. Where would it move it to? Not right 5. Huh? Where? Down 5, yeah. Yes. We have forgotten transformations, I see. Okay? So y equals x squared minus 5. It's going to move it down 5 units. So we move it down to right there, right? 1, 2, 3, 4, 5. Okay, so I'm going to erase these points. We just used them to get that. So now we have y equals x squared minus 5, right?
Absolutely.
Now I have to take the absolute value of that. If I take the absolute value of that,
That's
yeah.
cool. I did not even.
Remember, it flips this bottom part up instead of this going down because we're taking the absolute value of all the values we put in for x. We take the absolute value of it to get y. Well, that means all the y values have to be positive. So it just takes this whole thing and it flips it up here. So 1, 2, 3, 4, 5. Okay, it's going to go like this. So my graph is this part right here. It goes like this. And that part's gone, right? Because it flips it over the x-axis. You take the absolute value of it, and it flips it over. Do you remember that now? Okay, that's what happens when you take the absolute value of a function. Okay, now, obviously, we can, if we put something outside the parentheses, like if I went like this now, minus 3, it would shift this whole thing down 3 units. And you can have stuff below the x-axis because you're going to take the absolute values in here, and then you can shift the graph down. And so it can shift down. So it's just that everything's inside absolute value, so everything's going to be above the x-axis. Okay? Now, the same thing holds true for a linear equation. Hopefully you guys all see this, that this is the equation I'm asking for. Everybody see that? Because I wrote with parentheses back there, and some of you can't see that. But y equals the absolute value of 1/2 x plus 5. Okay, anybody want to do this one? It's the same concept. Graph the line, take the absolute value of it. I am going to call on Coulter. Coulter, you're going to do this. So we're going to erase this stuff. Put that back up there. Okay. Go ahead, Coulter. Okay. Now, let me ask you this, Coulter. Your line kind of curves right there, right? What's the slope of that line? Oh, yeah. So, you know what? That's not a very good graph to do this on because it's way off the graph, isn't it? But it'll still work. We just got to extend our graph. Let's do this. Let's count let's count the x scale. Let's count these as 2's. So 2, 4, 6, 8, 10, 12. So that's 10, 2, 4, 6. Okay, it's 2. Can we do that? And so that's going to be 12, 14, 16, 18. It's going to be 20 out there. So I want you to mark it with using the slope formula. Okay, using the slope, y-intercept and slope. And then I want you to take the absolute value of it. Okay, go ahead. Well, erase that line. I want you to redo it. In fact, let's do the same scale going up on the y-axis. Let's go in 2's. Okay, so if you go up the y-axis in 2's, where's the y-intercept going to be? No, where is it? What does it say the y-intercept is? 5. So mark 5 on the y-axis. Okay, that's where it's going to be if we go up in 2's, okay? And then what's the slope? Okay, so we're going to go where from there? Rise over run. down 1 over 2. Okay, do that. Yeah. Okay, so mark some more points on there. Okay. We went up, every mark on there is 2.
Yeah, I know.
You go 2 over 4.
Oh, yeah. Oh, yeah.
So it'd be less of a.
Well, he went 2, down 2, and over 4.
Same thing.
Yeah, same thing. Okay, so there's that line. Now, take the absolute value of it. What happens? Someone help him out?
It flips.
No, not right there. The part below the x-axis flips up and goes over the part below the x-axis. What part's below the x-axis? Yeah, so it's going to flip over. Yeah. That's what makes the V shape, right? Okay? So erase that bottom part now. Okay, so my graph's going to look something like that, you guys, right? Because it just reflects the line up over the y-axis. Thank you, Coulter. Do we understand that now? Thought you guys understood it before and we didn't get it. We're gonna do another one. Okay. Okay, it looks like most of you guys haven't figured out. Some of you guys are still struggling with this idea of flipping it over the x-axis, aren't we?
No.
There's a couple of you.
So.
Listen, some of you guys are missing the x squared, okay? If I graph y equals x squared, it looks like this. You have 0, 0. You know, if you made a table of values, you put 0 in, you get 0. You put 1 in, 1 squared is 1. You put 2 in, 2 squared is 4. 3 in, 3 squared is 9. So when they've just got the old bell schedule up, you guys. So that was the late one. This is when we'd actually usually be starting class. Okay, so we go 1, 1, and it would also be negative 1, 1, 2, 4, 3, negative 2, 4, and 3, 9, and negative 3, 9, right? This would be our parabola. Yeah, now, what happens when you minus 8 from a parabola, or any graph? It shifts down 8 units. So this thing goes down to there. Well, that's down to 9, huh? Goes down. Great. Okay, down. Right there, and all right. It goes down. I'm going to redraw it. That's what I'm going to do. This thing's not dragging down. Okay. Okay, so we go down to negative 8. And so this is where we are at. And you guys can think of this as going over 1 and up 1 from there, over 2, up 1, 2, 3, 4 from there, over 3 and up 9. And you can think of it this way. And there's the graph going down like this. But then what happens is when we take the absolute value of it, all the part below the x-axis flips over. It goes like that. So this green one is our graph. Do we understand that now?
Yes.
Okay. We're taking the absolute value of it. So all those y values became positive values. Okay. Let's do this. Y equals the absolute value of 3/2 x minus 2. The absolute value of 3/2 x minus 2. If I took those absolute value signs away, what kind of equation is that? Linear. So graph the linear equation, then what?
Then you absolute value everything underneath you.
Yeah, there you go. Okay, go ahead and do that. Okay, so you guys, I know that the y-intercept is negative 2. I have a slope of up 3 over 2. And so I have this line that's going up like this. It's down like this. However, I know when I take the absolute value of it, it's just going to reflect it. Anything below the x-axis is going to flip over and go up this way, right? So it's going to make this V shape like this. This is the graph of the absolute value of that function. Everybody take your calculator now. I want you to graph that in your calculator. The goal on these absolute value is to make sure you understand why you get a V shape on the linear equation, why you get that W shape on the quadratics. It's because it reflects that bottom part. You take the absolute value of it, it makes everything positive. So it's going to reflect it over that x-axis. Okay? All right, now, the next type of function that we need to talk about is a rational function. Okay? So we talked about these earlier in the year, but we're going to do it a little bit different this time. We are going, well, you almost have to do it the same right here. We had something, let's take something like this. The absolute y equals x plus 1 divided by x plus 2. Okay? This is a rational function. Rational functions cause you to have asymptotes. If you remember right, a rational function can have as many vertical asymptotes as you want by, depending on what the degree of the denominator is. Okay, the higher the degree of the denominator, the more vertical asymptotes you could possibly have. But if you look at this right here, the vertical asymptotes occur where the denominator is 0. In your groups, decide where your vertical asymptote for this one's going to be. I'm going to give you a minute. Go. Talk. Okay, where would the vertical asymptote be? Okay, negative 2. That's right. Because when x is negative 2 plus 2 would make 0 in the denominator, and division by 0 is undefined. So we are going to go to negative 2, and we are going to draw a dotted line along x equals negative 2. That's going to be our vertical asymptote. Remember, an asymptote is an imaginary barrier that the graph gets closer and closer to but never touches. Okay, vertical asymptotes, the graph will never cross it. Now, sometimes with horizontal asymptotes, they do. Okay, but that's how you find vertical asymptotes. You just set the denominator equal to 0. I want everybody to write that down. To find a vertical asymptote, set the denominator equal to 0. Now, you guys, earlier in the year, I gave you a paper on how to find vertical and horizontal and slant asymptotes. See if you can find it in your notes really quickly. I'm going to give you a minute. Okay. So we found out that I didn't give that paper to you at the first of the year, those of you listening to this at home. So we're going to talk about rational functions more on Tuesday. However, right now we're going to do number 7 on your homework assignment. Okay? So number 7. What does that function say? Say that again. X plus 3 over 4x plus 2? Let me see it, please. Okay, so x plus 3 over 4x minus 2. And this function is called f of x. F sub 7 of x, because it's problem number 7. We'll just call it f of x right here. And we're supposed to graph it for the domain where the absolute value of x is less than or equal to 4. Hey, this is interesting right here. We're supposed to only graph it for the domain where the absolute value of x is less than or equal to 4. So I want you to think about which numbers could we put in for x, take the absolute value of it, and get a number less than 4. Okay, say that again, JD. All the way negative? So you're saying from 4 to negative 4? What do you guys think? JD's saying this right here. He's saying all numbers between negative 4 and 4. Would that be correct?
Yeah.
It would be. Because if you put negative 4 in there, or if you put negative 3 in there, let's say, and took the absolute value, that's going to be less than 4. What about negative 5, though? Okay, because negative 5 would make it, if you take the absolute value, you get positive 5, which is not less than 4. So it's going to be all numbers between negative 4 and 4. So we're only going to graph those numbers on that domain. So right here, you guys, we are going to go to 1, 2, 3, 4. I am going to put a red line there, meaning that's our boundary that way. And then at negative 4, that's our boundary that way. We're only going to graph the part of this function that's between those two lines, between negative 4 and 4. Okay, now, let's find the vertical asymptote here. I just taught you how to do that. So everybody tell me what the vertical asymptote is. I'm going to give you a minute on that. Talk about it in your group. Okay, what did you guys get? What? Okay, some of you guys are saying 0.5. Why is it 0.5? Why, Trayson?
Set equals 0, you plus 2 over 4x equals 2, and then you divide by 4.
Okay, and you get 0.5. Another way you can think about it, you guys, is 4 times 1/2. What's 4 times 1/2?
2.
2. And what's 2 minus 2?
0.
0. So the key was you set the denominator equal to 0, and you solve that equation, and you'd get x equals 1/2. So there is a vertical asymptote at x equals 1/2. In other words, x cannot be 1/2. So we're going to put a vertical asymptote. We're going to make a dotted line right here at 1/2. Okay? And that's our vertical asymptote. All right, now, there's a way to find horizontal asymptotes. I'm going to teach you that on Tuesday, but I'm going to teach you on this one right here. What's the degree of the polynomial in the denominator right here? This is key. Everybody listen. What's the degree of this numerator right here? First degree, right? It's a linear equation. So it's degree 1. What's the degree of the denominator? It's a first degree. It's 1. Write this down. Anytime the degrees of the numerator and the denominator are the same, then there is a horizontal asymptote. And to find that horizontal asymptote, okay, when the degrees of the numerator and the denominator are the same, there is a horizontal asymptote.
How do we know it's
And you find the horizontal asymptote by taking the coefficient of the highest degree term in the numerator and divide it by the coefficient of the highest degree term in the denominator. Don't write that down. I'll give you a paper that says it. Everybody look up here. What's the highest degree term in x plus 3?
3?
No, what the highest degree term is x, because it's x to the first power. That's 0 degree. The 3 is 0 degree, right? So that's x. What's the coefficient of x? 1. Does everybody understand that? You got to look right here. The coefficient of this x is 1. What's the coefficient of the denominator? 4. If we divide 1 by 4, that's where the horizontal asymptote is going to be. So there's going to be a horizontal asymptote at x equals 1/4. So we go to 1/4, which is just above, just barely above the x-axis. And that right there, y equals, I put x. I should have put y. Y equals 1/4 is the horizontal asymptote. That's all the asymptotes it has, this function right here. Some functions, if the degrees are, if the degree of the denominator is higher, it could have more vertical asymptotes. Also, but there can only be one horizontal or one slant asymptote or neither one of them, and we'll talk about that on Tuesday. Okay, so now what we do, to graph this, we can plot some points. We're going to make an xy table. Now, what points do we want to choose for x right here? What numbers would we want to put in for x? Well, our domain is from -4 to 4. Do we want to choose numbers between there? In fact, we could probably choose -4, -3, -2, -1, 0, 1, 2, 3, 4. Let's see how these work out. We may need to choose some fractions in between those numbers, but that's going to be a good place to start with. So we're gonna plug these in. What's -4 plus 3? -1. And 4 times -4 is -16. Minus 2 is -18. So that comes out to be a positive 1/18. So at -4, I'm going to get 4 comma 1/18. So I'm going to put that on the graph right here. I'm going to go to 4 comma 1/18, which is going to be barely right there, right? -4 comma 1/18. I put that little blue dot on the graph. Okay, if I put -3 in there, what's -3 plus 3? 0. I know then at -3 right now, 0 divided by whatever the denominator is going to be 0. So at -3, it's crossing the x-axis. So I'm going to put a point right there for -3 comma 0. If I put -2 in there, -2 plus 3 is 1. And 4 times -2 is -8. Minus 2 is -10, so -1/10. So -2 comma -1/10. So I'm going to go to -2 and barely be below that. Okay, -1. -1 plus 3 is 2. 4 times -1 is -4. Minus 2 is -6. That's going to equal -1/3, right? So we're going to go to -1 comma -1/3. Then we're going to put 0 in. Well, 0 is just going to come out to be, no, it's not going to come out to be 0. It's going to come out to be -3/2. Oh, the numerator is 3. And the denominator is what? 2. So 0 comma -3/2. So -3/2 is -1.5. So I'm going to be about right here, right? Okay. Now, guess what? That's all the numbers I have between this vertical asymptote and our boundary on the left. This graph goes like this. Okay. In fact, I would have to get a lot of numbers, but that's going to get closer and closer to that vertical asymptote, but it's never going to touch it. Okay, and then it's out that way too. But we're only going to that. We were only going to right there, so we don't need to put an arrow right there. We're only going to that boundary point. So that's that graph. So let's go to the right side of that vertical asymptote. Let's go put in 1. What do I get when I put 1 in this graph? 1 plus 3 is 4. It's at 11:05. Who skits? Okay, just a second. Let me tell. Okay, yeah, 10:05. Hey, you guys, listen. I want you to work on this assignment. Finish plotting these points right here and graph the part of the graph that's going to be on the right side of this. Okay, and on Tuesday. Oh, we forgot to correct that assignment today. Okay, we're going to do this. We're going to correct the assignment on Tuesday. I'll see you.